So, ladies and gentlemen, I would like to start this evening with welcoming you all, and especially dear Peter Leibinger, dear Markus Wehner, dear Lars Grünert, dear Berthold Schmidt, dear Hagen Ziemer, all from Trumpf or the Trumpf Foundation, dear colleagues from the University of Stuttgart, dear guests. It is a great pleasure to welcome you here at our university, at the University of Stuttgart this evening, in a year that could hardly be more fitting to the topic of today's evening. As you all might know, 2025 has been designated to the International Year of Quantum Science and Technology, a global invitation to reflect on how quantum physics has shaped not only our science worldwide, but increasingly also our technological, economic, and cultural future. This evening, created in partnership with the Berthold Leibinger Stiftung, beautifully embodies this spirit. It brings together science, industry, art, which at least I find is very special, and society to look at quantum technologies from all angles, their foundations, their promises, and their implications. Allow me to first warmly acknowledge the distinguished members of today's panel. Dr. Heike Riel. We already said hello. Professor Joachim Ankerhold from the University of Stuttgart, Heike Riel from IBM and President-elect of the German Physical Society, Roman Lipski, our artist, welcome, and Dr. Ariane Kripper from Parity Quantum Computing in Austria. A warm welcome. For us here at the University of Stuttgart, quantum technology is not only one topic amongst many, it is one of our profile areas and a field in which we have built internationally visible strength. Here in Stuttgart, quantum technologies thrive because of a unique ecosystem. The Center for Integrated Quantum Science and Technology, IQST, of course, run jointly with the universities of Ulm and Tübingen, which I believe is not right, but with the KIT. So I don't, this is probably to check if the rector knows what he's reading. Bringing together more than 100 researchers working across physics, engineering, chemistry, and the life science. IQST has become a model of interdisciplinary collaboration and talent development, and of course Joachim Ankerhold is a living legend of IQST here amongst us, and Professor Stephanie Bartz, hello, is from our university currently one of the directors of IQST. Then we have the Center for Applied Quantum Technology, ZR-Quant, which provides state-of-the-art infrastructure, a so-called, this is very German, Artikel 91b Gebäude. And here we have all ingredients for researching on quantum sensors, quantum photonic components, and scalable quantum systems. It is a place where fundamental science takes place, but also where fundamental science already meets industrial application, and this is once again something which I believe is very special. Our coordinated research programs, including QSense, dedicated to quantum sensing, and Q-Photon, advancing quantum photonic technologies, demonstrate how deeply quantum research is furthermore anchored across our university and how closely it connects to partners in industry. And of course, the ecosystem is not only the ecosystem of the different research platforms that we have at our universities, but it is an exceptional network of quantum active companies that we have here in Baden-Württemberg and around, from global players like Trumpf and IBM, which I already mentioned, to innovative newcomers. Can we name Quant still as a newcomer? I think we can, but a real scale-up, I would say, with Michael Förtsch here moderating the panel afterwards. This tight coupling of research and industry is exactly what Europe needs to translate quantum science into real-world technologies. And at the University of Stuttgart, we take pride in training the next generation of quantum engineers and scientists. Our curricula increasingly integrate quantum technologies across physics, computer science, and engineering, which is exactly what the University of Stuttgart profile is, ensuring that our students are ready for a world in which quantum competences will be a key driver for innovation. As quantum technologies advance in computing, sensing, and communication, and also beyond, they challenge us also to rethink what is technologically possible. But they also invite us to ask deeper questions. How will these developments shape society? How will these influence culture, creativity, and our understanding of nature itself? And this is also a topic of this evening. Events like tonight's are essential because they bridge these worlds. They help us to build a shared language between science and the public, between industry and academia, and even between physics and the arts. And they remind us that quantum, or the next quantum revolution, will not only be a scientific milestone, but probably also a cultural transformation. The future that quantum technologies promise is rich, complex, and hopefully full of opportunities. At the University of Stuttgart, we are committed to shaping that future with excellence in research, of course, but also with strong partners by our side and with a vision that combines scientific discovery with societal responsibility. Let me close with a heartfelt thanks to the Berthold Leibinger Stiftung for the trust and partnership that makes events like this possible, to our colleagues from the physics department for their dedication and organization, and to all of you for being here in this hall, for joining us, and for celebrating quantum science this evening. And I wish us all an inspiring evening, stimulating discussions, and fresh insights into the fascinating world of quantum technologies. Thank you.
Also, a very, very good evening from my side. It's a pleasure to be here. And it's a very special evening, as you will find out in a minute. But first of all, what is Leibinger Begegnungen? It's a series of talks that provides, as we feel, fascinating insights into the diverse funding activities of our foundation. And of course, these insights are gathered really through meeting great minds. This is what we try to provide. And I'm looking forward to the evening ahead of us in this context. Today is the 95th birthday of my father. I cannot imagine a more appropriate way to celebrate my father's birthday than an evening like this. My father was as much an inspiration in my life as he sometimes was a difficult father. However, in the end, it's the inspiration that I remember him most for and that I'm most grateful for. The breadth of topics that he inspired us with seems endless. From architecture to literature, from history and philosophy to religion, from technology and physics to music. There were no topics that he would not find interesting and that he would not try to deeply understand. In the end, it was his endless curiosity for this incredible world we live in that drove him in everything he did. Curiosity, as I described it, was one part. The emphasis on the human relationship and the reflection of the human condition was the other. He had, in my mind, an enviable ability to get into contact with others. Those who knew him will know what I'm talking about. Ultimately, what we do tonight is exactly what inspired him. I personally have been involved in physics all my life. Even though I studied mechanical engineering, which I'm grateful for because it opened vast horizons for me, it is essentially physics that became the core of my work life. Without really realizing this in the beginning, it was quantum physics that was the great game changer for our company Trumpf and also for myself. Of course, the laser is an instrument of quantum physics. So it was only logical that at some point we would also engage in true quantum physics. Quant, it was mentioned already, the company that Michael Förtsch is the CEO of, is one of the results of these efforts. I founded this company 5 years ago, is that correct? Yeah, yeah. 5 years ago, and in the meantime, it has become what I would describe a true startup in the sense that it is funded by Trumpf as well as by true VC investors from the outside. And I think it can become a unicorn in quantum physics if it is allowed to call itself a company that works in quantum physics. We can debate that tonight. It has pivoted twice, and the second pivot is a bit away from quantum physics in my understanding, but we'll see. Much is written and said about the relevance of quantum computing and other quantum physics applications. Much of what is written, excuse my French, is complete bogus. But what is true is that quantum physics will impact technology, the economy, and our societies around the world in a profound way. To me, it has every ingredient of a Copernican revolution. So it's of course only fitting that this year is the International Year of Quantum Science, and the Bertolt Leibinger Stiftung is a distinguished partner of the International Year of Quantum Science. With the Bertolt Leibinger Innovationspreis and Zukunftspreis, we have two prizes that we award every other year that revolve around the question of lasers, laser applications, and as a advertisement section here, you can apply for these prizes or for the nominations and could be considered. Groups from around the world apply. Again, it's a pleasure to be here. I'm looking forward to the discussion. I'm looking forward to learn what is new. But before we have this pleasure, Eddie Fang, an artist, will perform for us a performance based on quantum computing, and I'm very excited to hear that. Thank you very much to the University of Stuttgart for your excellent cooperation and for making this evening possible here tonight, and especially to the employees, these thanks, of the Physics Institute for your help. Thank you very much. Looking forward to your performance now and then to the discussion.
Thank you. Are you continuing? No.
No, that's all. Yeah.
That's all right. So you can maybe stand up and we give an extra applause, round of applause. Fascinating. So when I saw this, my first question to you, I mean, I'm the moderator, right? So I'm allowed to ask question whatever I'd like to. This is your, so the first question I have actually is, what actually is the interest behind you that making artistic work related to quantum?
For me, can you hear me? Yeah.
I think.
Oh, right. Before getting into the subject of quantum, I've always been fascinated by the notions of noise, randomness, and entropy. And I'm interested in how we relate to noise as something undesirable and unwanted, and unpredictable as well. But then it gives useful and valuable information, especially when it comes to fields like encryption and security, as I started to learn about it. And this also led me to explore random fluctuation more deeply, as well as how randomness has inspired cultural and philosophical interpretations that aims to contrast with deterministic worldviews. And then I started to become more drawn to quantum physics, which diverged from classical physics, and that it might offer entirely new ways to think about computation and technology. The physicists I met have told me that quantum randomness is so far considered truly random, and that idea motivated me to explore quantum randomness as a source for generative art, and this composition piece is one example.
So we touched already a lot of topics here, like quantum being truly random. Mr. Leibinger, we talked about this a lot. But it's fascinating how this true randomness, which only nature can provide us, is now turned into art. Great. I mean, I was working in the laboratory trying to convince the world that the quantum randomness is truly random. But what challenges have you encountered when basically going on this process, on this journey?
Obviously, it was a huge topic, the whole quantum technology in itself. Well, it lies at the intersection of quantum physics, the engineering, as well as computer science. I tried to read a lot. Also, at the beginning, try to navigate the right books to read was a challenge. But then I tried to visit as many, well, I tried to visit labs, the photonic labs in Berlin and in Stockholm, and also when I had residency in San Sebastian. And I really tried to speak to as many physicists I met. And so integrating all these complex topics into my own artistic practice in itself, which has been the electroacoustic and intermediate arts has been an ongoing practice that I work with, and so try to integrate that has been rather new, and there is not a lot of precedent to rely on. And once I began to grasp the science more clearly, another challenge emerged related to how to communicate these ideas to art and culture, to artists and curators. There's a constant need to translate between languages of art and science, because these fields, each of them has their own terminologies and assumptions, metaphors, and modes of understanding. And so in this work, I aim to use materials that resonate with both artistic and scientific worlds. Sound artists like myself often work with electromagnetic interference as a material for creating sonic and textured experience. Similarly, the single photon source process use the infrared pump to generate signal and idler photon pairs, which I seek to highlight the common ground between how scientists and how artists work. So here I made sonification of the photons, translating quantum phenomena into perceptible sound, layered on top of the electromagnetic soundscapes, so that hopefully the work will speak to both worlds.
I have a question to the audience. Who is in quantum some way or the other? Well, everywhere in a quantum world, but that's not the point. Who is working in quantum? Quantum mechanics, something scientist, or maybe founded a company, something strange. Okay, I guess there were a lot of terms in your explanation, and I was deeply impressed also when we spoke before how deep you actually went with your scientific knowledge to translate this into art. My really last question, didn't see a lot of hands coming up, but maybe some of our audience wants to educate themselves. What's the best book that they should read? You can tell us later. Thank you very much, Eddie Fang. All right. I was always waiting for this moment. Quantum technology, I think it's not an easy topic, right? And I would say that if we would not speak in front of such an distinguished audience, there is always this question whether it's science fiction or, and I brought devices to travel through the evening, or it's some magic dishwasher tables which have quantum effects to clean your glasses. So you already see where this is going to walk to tonight. What's on the agenda is we want to clarify the truth behind what can quantum do, what can quantum not do, what's in the realm of myth, and what can we expect from this technology to come up with the next years. I'm moderating, but we need experts. And therefore, welcome with me on stage four distinguished experts on this topic. Dr. Heike Riel, IBM Fellow, Professor Dr. Joachim Ankerhold, Dr. Ariane Kripa, and Roman Lipski. Just a quick intro to the audience. Make yourself comfortable. We have 90 minutes, so maybe you already pulled the glasses towards you. It might be that we are ending in a long discussion. Everyone should pick a mic. Great. So I thought it's better that you are going to introduce yourself because you can do this best. But I have a little of a challenge here. You have one sentence to explain who you are. And if you're not using the word quantum, you get an extra bonus. I would start with you, Heike, and you should use your microphone.
Okay, can you hear us? Okay, good. So, I have the best job because I can work with super smart people to develop the next generation of new types of computers which can solve problems that classical machines can't do.
Perfect.
More energy efficient.
And I am the person that is using the computers that I can mention. Not really. So I'm a software engineer, so I've been using computers, classical computers, to try to solve very difficult problems. And now I'm trying new special computers to try to solve even more difficult problem and see where we can really go.
I guess we're going to figure out what's so special about these computers tonight. Joachim.
So you asked us to tell your little boy why to choose the field. Yeah, I remember this. So I would say to him, well, see, theoretical physicists is very crazy folks. Playing all days long or most of the day with toys as big as a cosmos and as small as atoms. Some of those toys they developed on themselves. So I warn you, never go to this field.
Very good. And Roman?
It should be just a one sentence, right? So, first of all, I'm very glad to be here. Thank you for having me. And so, I'm a painter from Berlin, very curious painter, and probably a good one.
So you see, we have a huge variety from scientific experts to industrial experts to artists, and I think that's the best thing to start the evening with. Before we start, the rules are, so we are covering quantum technologies in 4 categories. The first category is, please give the audience a general overview. What is quantum technology? The second one, let's be a bit more fair on what's the status quo of this technology, how mature it is. The third category is going to be what kind of application. I mean, technology is nice, right? But in the end, technology also indicates that there is some return on invest. I was always asked this by the investors. So what's in the end the business applications behind all these efforts? And the last one is about the impact of quantum on our society. The scene will be as follows. We have these 4 categories, and each, so I was very fair and gentle with our panel. They received 90% of the questions. The last 10% of the questions, the last 10% questions are the entering into each sections, which I call, basically, it's a flashlight. It's one question, and you only have one word or one indicator to respond on this question, okay?
Indicator?
You can say yes, no, maybe, thumb up, thumb down. It's not about discussing, it's just giving your gut feeling in a very short amount of time what you feel about the question, what you think about the question, okay? I didn't tell them before, this was the mean part in the preparation. Okay, let's start with the first one. Let's go on a general introduction. Before we start with this, a short story. When we've been asked from the BMBF a few years ago, now it's the BMFDR, Bundesministerium für Forschung, Technologie und Raumfahrt, to participate in the Future Academy, we had a group of students and we sent them downtown Stuttgart. And the question we gave them was, ask random passengers what they would do with their smartphone if it contains atoms.
It doesn't?
What would you think? How many of the completely spontaneous asked people have responded, I would throw it away?
95%.
100%?
90%.
A lot.
So actually, it was 70%. We see that already the broad audience is a bit more educated, but I thought I'd bring a new sign. But what it tells that the education of the broad audience about what quantum technology is essential, that we are not creating myth and fear about something that we truly can't understand by making observations on our daily life. Now, coming to the first question after, thank you for joining the first flashlight. Now we come to the more elaborate questions. And I would start with you, Joachim. So, I mean, quantum technology in general, as a general topic, arose quite some interest in the course of the last 10 years. What would you say? Is it an extra genius buzzword to get more money into science and into companies? Or what's the belief behind why this can become an industrial revolution? And maybe you can also elaborate a bit what kind of fields are going to be touched.
Okay, sure. But let me say, go back 100 years in history, because this is exactly the time when the quantum mechanics, the theoretical framework for quantum mechanics, was formulated, and it soon actually developed into technology. So already after the Second World War in the 50s and the 60s, quantum technologies had been developed, and we are surrounded by technologies which are based on quantum. Think about your cell phone, think about your computer, think about lasers, think about medical diagnostics like MRI. All these devices that are so common in our daily life are based on quantum mechanics. Quantum mechanics is not, I always emphasize this, is not a particular field in physics. Quantum physics is the basic formulation of all of physics. Classical physics is emerging out of quantum physics as in a particular limit. Special relativity as well. So quantum physics is the foundation of everything. Okay, so this is something one has to realize. When we are doing physics, when we are talking about technology, then we have to talk about quantum physics. When we switch on light, the new LED sources, this is practiced quantum physics. Yeah? So what we are doing now in the 21st century is we want to exploit and make accessible the wavy nature of quantum mechanics. So quantum objects are hybrids. They are massive particles on the one hand. On the other hand, they are waves. And waves can have properties like interferences, superpositions. They can overlap. And they can have wavy patterns that the individual waves cannot have. And this is something that we now want to exploit. And it's difficult. I mean, think about a plain lake, and you create a wave by just throwing a stone into the lake. And you throw another stone, and what emerges is a wavy pattern. That's fine, you can control this. But now consider the lake of Constance, and you want to control the wavy pattern on the lake of Constance. Now that's a challenge. Or go even further to the Baltic Sea. So this is somehow the challenges that appear when we strive to develop quantum technologies based on the wavy nature of matter. And currently the belief is that there is 2 or 3 basically basic fundamental fields in which this technology can provide breakthroughs. This is quantum sensing, this is quantum communication, and this is quantum simulation and quantum computing, basically, simulation and computing as one field. We were going to talk about this in more detail, I guess, yeah, but it's still, let's say, not a technology which you can buy. We are currently developing technologies, this technology, but I remind you only about the transistor, which was invented around 1950. And when is it then that, say, computers became common devices for everyone? 40 years later, I must say, about 1990s, beginning of the 90s. So it took 40 years to develop a bulky transistor and to integrate into an integrated circuit and to come up with a computing device that everyone can use, or even a cell phone. So give us some time. And then we are certainly coming out of this. So that's for the moment, yeah.
So the conclusion is we have 3 fields, you said? Communication, sensing, and computing, and we need time. That's good. That's good. Heike, you were in one of these fields, quantum computing. And you're working for one of the leading companies in that field. I say this, then you don't have to say this. why is everyone out of a sudden? I mean, Joachim just said, give us some time, but if I'm looking on the media, the status that's sometimes indicated looks a bit closer to the actual point in time where we are. So what, in your opinion, arose the sudden interest in quantum computing? And would you say this is justified?
So when he said 40 years, then I thought, when was the idea created, right? The idea was created in 1981, when Richard Feynman had the idea of building a quantum computer, because we can't simulate molecules, we can't simulate materials very well, and we need computers which are based on the same physics. Then these sophisticated and challenging tasks we want to solve. And I guess he was super frustrated as a researcher not being able to solve these things with a classical computer. And I call it sometimes out of frustration, you really do a great invention, right? And I think this was probably what happened. He came up with this brilliant idea, let's build a computer which is based on quantum physics. He did not know how to do this. He had no idea how he would need to do it. And then I would say then we still need theoretical physicists, right? Because the theoretical physicists came in at that time and they spent a lot of time over the next probably 20 years to just figure out how to build such a quantum computer. What is a qubit? How does a qubit need to, what the properties of a qubit? What are the characteristics of a qubit? And then when this has happened, then lots of experimental physicists could get started and to look into what physical systems could make a good qubit, and then do all the basic work of inventing and developing and exploring the qubit.
I don't know whether everyone knows what a qubit is.
Okay, I don't want to go into detail, but the qubit is in principle the analogon of a bit of a classical computer, which is the unit of information, of quantum information you use for quantum computation.
Okay.
That good enough?
Thank you. So
I think that's, let me now come to your question, right? So because I think 40 years are over, I think basic stuff has been done. We have 10 years ago built like a 5-qubit computer. And at that time, suddenly this type of things were available to theorists to use them practically, to get also algorithms done and learn about them and further explore them. So I think it's fair to say we made big steps forward, and there is computation which can be done. And it's accelerating the progress because there is now much more investment flowing into it, because there is a super high potential of really building soon a computer which can solve a valuable problem, economically valuable problem. And that's why I think it's fair that there is excitement around it. Yeah, let's leave it this way. We dive deeper into it.
We're going to touch the point of investments in that field later on. But thanks for giving us a judgment on quantum computing. Ariana, I mean, you're familiar with these words, right? I mean, you're not shocked by the name qubit in the meanwhile. But, I mean, we heard about the story that scientists have to make themselves comfortable with the term qubit for 40 years. Can you give us a bit of an idea what was your first interaction point with quantum mechanics? How did you respond on that? I mean, why didn't you run away? I mean, sometimes people take the easy classes at the university, right? And when you also could comment on when you basically started diving deeper into that, when was it, and what progress have you seen?
So then I have 2 replies. One is quantum mechanics, and the other is quantum computing. Quantum mechanics, everything started with the book by Carlo Rovelli, which is a theoretical field.
Which one?
Carlo Rovelli.
We're going to distribute this later on, so you should start with this book.
Yes. It was called, I think, 7 Lectures of Physics. I didn't know anything about physics. And I read this book and I was shocked. I was like, wow, this is incredible. I want to do this. So then I really decided, okay, now I'm going to a university. Of course, the first year were a nightmare. I really studied days and nights. But I continued, and then every time it was really a transformation. At first, I wanted to study astrophysics, for example. Then I discovered particle physics and theoretical physics, and then I switched to that. And then while I was doing actually my master thesis in theoretical particle physics, another shock. This came from a YouTube video, actually, from a professor called Shaini Ghosh. I'm sure this is not the correct pronunciation. And she was giving a very easy talk about quantum computing. And before that, I didn't know anything about quantum computers. I even didn't know they exist. And this was 5 years ago. And again, I was completely surprised and shocked, and I decided, okay, now I want to do this. So then, fortunately, back in the university, there was one course on quantum computing, and it was a bit weird because there was no actual software, everything was on paper. And I discovered, now thanks to IBM, Qiskit, that is basically an online platform that you can use, all of you can use, and you can really program and try to study and find out the language, so you can see how you can manipulate these quantum bits or qubits. So after this, then I did my PhD in quantum computing, again, still with this physics input. And now I'm still continuing in these fields. There is still physics, but also quantum computing.
So basically it was the origin, again, was a book that hugged you, and then you was drawn away. And actually I'm very glad that you came to the right side of physics. You tested all the fields, and I would say quantum physics is the right one. Right, Roman, on the last question in this round to you, you are the artist, right? I guess I was really fascinated. We come a bit later on what you exactly did, but can you explain how your interaction with these, not very well-known field of quantum technology, quantum mechanics probably, was? And can you give the audience a bit of an idea how you came across the idea to use this technology for art? And how actually do you see this? Is it like I'm painting and the universe helps me, or how would you see that?
Not really. Okay. First, I'm very impressed of your answers. I prepared very well for today, but already I lost my part. No, not really. My story is a little bit a love story. I find the way to quantum physics. I find over the AI, and the way to AI, to artificial intelligence. I created the kinds of concept was some kind of reaction of a creative crisis. And so first of all, as a classical painter, I find my way to technology or implement technology in my art through a very human weakness, creative crisis. AI indeed used in a very special way as a creative tool helped me overcome the crisis. And the concept became some kind popular, so that one day I got an invitation to visit IBM Research Center in Zurich, where I met my first quantum physicist live there saw in my life. And then before, I have no idea about quantum. I heard, of course, I read a little bit about, in the newspapers about quantum computing, about things like this. And so, after just one day, I fall in love with not with quantum physics, but with the atmosphere, with the possibility, or with the possibility to be a part of something very, very new and not usual. And as an artist, it's worked for me like for my imagination. It's worked for me. It was a kind of a promised land. as something completely new, a new change to improve myself, find the new horizons, escape from the routine, and be much more creative than everyone can be. And so the scientists there, especially Dr. Walter Ries, helped me, asked me the simple question: can you imagine combine your AI muse with a kind of teleportations idea? And of course, I was so happy. I agreed. I said, yes, of course, I wish. And in my head, I have a picture from Star Wars, the "Beam me up, Scotty," something like this. And so this is the way I find quantum in my life. And so actually, what I'm doing with quantum, not really with quantum computing, but with some quantum algorithm, I simulate some processes in order to create some visuals, a new picture. My wish is at least to be a painter, very innovative painter, using special effects to create new landscapes, right? And the universe not really help in this matter. It's make everything complicated.
So it was teleportation, a visit with a scientist at IBM, and something that hugged you, but it's hard to express. I see this, but there was something. One add-on question. Yeah. Was it the technology when you first saw a quantum computer, or was it the fascination of the potential applications?
Both, I will say. Hardware, the quantum computers, or I got some insights. I could. So first time a quantum computer, the quantum processor, and of course the hardware. It's look impressive, and it's like a very beautiful objects. And then also the whole topic, the ideas about entanglement, about superpositions, and all this stuff is amazing, inspired. And so quantum physics as an inspiration, and also quantum computing as a tool.
I mean,
yeah, may I ask a question to him?
Yeah, of course. I mean, this is makes my life easier.
You started saying that your first encounter with quantum physicists, yes. So with the scientists, not with the science, but with the scientists, was something that was extremely intriguing to you. What was it? What was have you some special aura? No, yeah, like was it the way we interact? We do so. This is just interesting.
Yeah. Of course, this is the human aspect of quantum physics. Probably everything started and will continue by humans and with humans, and so with persons. And the scientist was very open-minded, very open and able to thinking abstract, and it was what flashed me the most, because I am abstract painter and abstract ideas is my topic, and they was able to follow me, to follow the abstract ideas. There was not really, I felt myself very comfortable because they didn't ignore my even crazy or stupid ideas. Mm-hmm. They catch the idea and try immediately to play with the ideas, and in order to find something interesting in that.
Fantastic. Has everyone here in this room seen a quantum computer? So who has seen a quantum computer? That's the better question to the audience. Okay, so I'm not shocking you with the next picture. That's the technological beautiness of a quantum computer. But the actual question, so we are switching now gears, coming to the next section. We're coming to the status quo. And I guess I'm not telling secrets, especially to you. Stuttgart is the place of many technologies. We heard about the laser and how the laser found probably one of the best applications by cutting shield metal. There has also been another tiny invention here in this area, which is the car. And the flashlight question to the audience is, So, when we remind ourselves, by the way, everyone who is not from Stuttgart, go to the museum here, because it's not about the brand, it's about the history of the car, and it's really amazing to see how technology basically progressed over the years. But when we compare the status quo of the quantum computer with that of the car, the question to you is it more like this picture? This is when Carl Benz started the first combustion engine. Or are we already at this point? Bertha Benz took the car of her husband and drove from Mannheim to Pforzheim. Or are we already in the area of the Model T, where we have a serial production of the car? One word. Heike.
I take this one because...
You don't have to explain it. We're coming to this. So Heike votes for this. Ariana?
I take the first.
Okay. Oh my God, I need more hands.
I take the second as well.
Okay, so this goes higher.
It's also my choice.
So this one? Okay, then I have some scotch tape to remind ourselves that this is now the official status of the quantum computer. But going into detail, coming back to you, Roman, I mean, we talked about your motivation, but let's be honest, you declared that this is already at the stage when Bertha Benz drove from Mannheim to Pforzheim with the car. Now you've invented probably a new category in artists, right? You use the quantum computer to paint. You call this the quantum brush. What would you say? How much did it help to say it's the quantum brush, or how much was it then these truly fascinating pictures? So are we here? Are the pictures already basically self-speaking, or are we still explaining why actually it's beneficial to use this?
So artistically, I will say we are some earlier. We are at the point where the wheel was invented. And very basic one. Yeah, we are dealing with some very abstract ideas. And so first, some insight was a little bit mixed. I started. So I asked myself. I asked also James Wharton for the question: do we really use quantum computer to develop some visual, some picture in the past when we started to cooperate? And his answer was not really. We just ran some starts, but it didn't make a sense because the algorithm I'm used, the quantum algorithm was not really developed to create a picture. So I adopt a kind of quantum software, quantum algorithm to create picture, but the software was not developed for this reason. And so, but anyway, with some kind of artistic invention and fantasy, I was able, and still I produced, I create a lot of quantum picture. The quantum video I presented this year here by the event earlier then was based on this quantum blur software. And so then what I did is I didn't use quantum computer to create art. I just simulate some quantum processes, yeah, or some quantum processes, and also some this is the way what I'm doing, how I'm doing quantum art. And the second software I'm using actually, and also Ariane is also the developer of the software. We
didn't know.
Me too, as an artist.
We are working together.
Oh wow! I think that's a secret.
Secretly.
It's really cool because me as a painter, there was at the beginning of September we published, there was published first scientific paper, my scientific paper, where I was a part of a team, and this is in the topic of quantum software. Absolutely amazing. And so with Quantum Brush, this is a little bit more than Quantum Blur, because here I not only simulate some processes, some quantum effects to change, to transform the colors, but here I'm very deeply in the matter, and I try to adopt the idea of quantum or the effects I can get with the software in the analog paintings. I try to create a kind of hybrid system where the colors developed by, for example, effects created by Ariana is Heisenberg brush.
What's Heisenberg brush and quantum brush?
Heisenberg brush.
Heisenberg would brush. How would you know how Heisenberg would brush? Kidding. I understand. Maybe you
Read
can explain
the paper.
What's the difference?
So the Heisenberg brush, for example, the quantum effect allowed me to develop a very unique and special color palette, which is not really, I can compare it to the classical way to mix the colors on the palette, but this way to get the colors and is some different. And what my wish is, or what I'm hoping is to one day to describe or find a new way to create, of course, a new artistic style, right? Quantum, and I'm not alone. There are so many in between. There are much more quantum artists. Mostly, they are coming from science. They are scientists converting to be an artist, and so they are actually on some kind of. There is a process, and the quantum art scene will develop. It's bigger and bigger.
That sounds very visionary. We're going to continue on that one.
Can I add something before we continue?
Yeah, of course.
Also related to this quantum brush. So it's not just the two of us. We really worked together as a team. And it was very interesting because we could really put both perspectives, so the scientific part and also the artistic view. So we could really create something that has a meaning, and it's not just let's try and run an algorithm on qubits because it's fun, but there is really a physical meaning behind it, but also looks very nice, and there is also a study on the creative process. So really what also Roman did to really use this to change and create basically new colors or new combinations of colors.
I'd like to follow up on this question because would you see the chance that we see scientific publications where the plots are going to be painted using that technology, illustrating directly the science?
Depends the precision that you want to achieve.
I'm looking forward to this publication because this would truly be an innovation inside the innovation. Heike, you were very transparent at IBM with your roadmap. I mean, we're talking about the status quo, and what I ever since admired you for is that you, on the one side, were bold enough to put a roadmap out. Second one, you're comparing your progress with respect to this roadmap, and this is not usual. Let's be honest, when you started and where are you actually standing? What do you promise your customers, right? I mean, you have a roadmap, which is now to everyone accountable. The other question is, how much pressure do you put yourself on by being so accurate? And I think these 3 points are a good proof point for the status quo of quantum computers, I would say.
So I think road mapping is kind of has been done in the semiconductor industry for quite some time, right? It helps really to have a focus, to know as an ecosystem also what the plan is, and to have all the supply chain and all the partners in this ecosystem also knowing what to deliver at which time. So it's kind of in our DNA, because we are semiconductor, I mean, we have a long history of semiconductor technology development, and so it's part of our DNA to make roadmaps. And I think we were very bold also when we put out the first roadmap to really promise to deliver on those milestones, which we had given like for 4 years ahead in time. We were the first. It was also very detailed, and it was probably also within IBM, oh my God, right? Now you have a roadmap outside. It's very ambitious. You don't have everything in your drawer and you can put it on the table when the time is there, but you really have to develop it and you have to work on it in a focused way. A very positive thing of a roadmap is not only for the outside, that if you deliver, you also create a lot of trust into your promises, into the technology, into also the next steps to come. And you have also suppliers who also can align with it, who can help to develop things, and also with the users, right? That the users who want to use and apply quantum computers also know what type of performance and number of qubits and logic gates I can run, etc., are available. Internally, again, it's also very important because it helped to focus the team, the quantum team, on the right goals. I mean, how do you motivate and how do you make researchers, brilliant researchers, work towards one goal? I mean, you can judge from your own environment at university how this works, right? So if you have like a roadmap and you are aligned behind that roadmap, then every individual, every smart individual can decide, is this what I'm currently doing helpful to deliver on the roadmap or not? Then you can give yourself the answer. And I think this internally is also actually a very good strategy process and a very good process of aligning everyone behind.
So just to give a bit of an inside view here, IBM set with your roadmap the benchmark for the community. There are often discussions, where are we with respect to IBM? The question is, would you wish for that others would follow you on this openness?
So first, many others are follow us.
Oh.
Right? They also they are under pressure to actually also make roadmaps. And they're also, I think we still have the very most detailed and most ambitious roadmap, which is published with many different details if you go in. So typically when we show the chart, we cannot even go through all the details because it takes an hour. So I think you also asked for pressure internally. I wanted to add on that it's for a scientist to develop these pioneering things and be ahead and have a brilliant team of everyone working towards one goal and achieving these things. That's actually a very, very positive pressure and passion and energy you can create. And so that's actually in that regard of course it's ambitious, and of course it's, there are milestones, etc. But it's a very positive pressure, and then it's a lot of satisfaction if you can make your check mark.
That's great, right? So these green check marks on, I can imagine, that's fantastic. Joachim, many say the hype is too big. Some say the hype around quantum in general is too small. I'm not asking you how to judge on this, but in all this curiosity and all this, how do you find the focus on your research, that you're not being drawn away by this attention that's currently sometimes overhyping things, underestimating? I mean, there are cultures that are usually continuously depressed. And how you basically ignore this and just focus on what progress matters?
You see, that's in a way, as a fundamental scientist, that's very easy. So in the morning at breakfast, when I go through the newspaper and I read what some colleagues or some companies promise or what they have claim, what they have seen, I'm just amused. And then I go to university and I do serious research. So, I mean, from the fundamental perspective, we know what we are doing. I mean, we are scientists, so we are serious people. We are, say, fascinated by the science we are doing. We are curious to discover new things. We are really emotionally attached when there is something new coming out. And then there is this hype that in a way, you see, we live in times where media promote those hypes. I mean, this was, say, decades ago, it was different. But these days, this is somehow how the game basically is played. And I mean, in a way, there's a good side in it. Yeah? I mean, first of all, it brings in attention. So an event like this, I don't know whether we would sit here when there weren't any say hype news in the media. So there is around the globe, people are now somehow talking about quantum physics, which I find fascinating because you see, when I was a student or a postdoc or a young professor, I mean, you see, it's a very, 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 very tiny community with whom you can actually discuss what you are doing. I mean, my family does not know what I'm doing. I mean, of course, they somehow know the words, but they have no idea what it means to go, let's say, deal 8, 9, 10 hours per day with very abstract mathematics. And this math has some relation to nature. Yeah. So in this sense, research is not much affected by this. Of course, I mean, you see, when we hear that Microsoft recently announced that they came up with a new type of qubit, and then some colleagues are speculating about the many worlds interpretation. I mean, this is all, say, just for the entertainment of the people. But it's not based on, and we, I mean, we are somehow can step back. There is one thing which I find, say, difficult. That's true, and this is the money. Because attention and hype also brings in money, because the politicians somehow realize, well, we have to invest in quantum physics, in quantum technology. And we all need money. I mean, theoreticians typically don't need that much, but experimental physics, and Heike, you didn't talk about the money that IBM puts on the table in order to let this program running. Yeah, but there's money, and this, there is a tendency to how should I say this, to compete not on a scientific level, but in the political arena. To attract most of the money and to somehow push the own field forward. And this is something that we as scientists, there I'm a bit sometimes disappointed, say, that scientists start to engage in this type of game. Yeah.
I couldn't have wished for a better answer to give a transition to the next section, the application. Let's educate our audience. The next point is that this is the tree of application. And, okay, this is the tree. Oh, sorry, I also have to show it to you. So it's a tree, right? It's an artistic, well, maybe not a so artistic tree. It's just I just put it out. And I have 10 applications. And the flashlight is all about, I'm saying what the eventual quantum advantage of the application is. And if you say it's true, you raise your thumb, and we're going to put it on the tree. Or if you say it's crap, we throw it into the bin. Okay?
That's a dangerous task.
Well, I initially thought we were going to burn the card, but then I thought maybe... Okay. The first is, and this was already here, what would you say? Better dishwashers with quantum effects, yes or no? It's up to you. You can all raise the hand or thumb. It's about...
Of course, no.
Okay, let's burn it. Second one, mind control with quantum sensors. Yeah. So you would say if we are not controlling it but measuring it?
Yeah, you can measure it. Measuring is okay.
Okay, so then we learned already something. So we can read the brain, but we can't influence it. So let's turn the question around. So,
I'm not sure whether you couldn't, but not with the sensor.
I mean, there was just yes or no. So let's flip it around to have something on the tree. Measure the brain activities and control the smartphone just by your thoughts. Is this something that can be reached with quantum sensors?
Let's stick to the measure the brain.
Microphone. Ah, you need the mic.
Measure the brain is okay. Don't go to
Measure the brain. What's
measure the brain signals much better.
And what do we do with it if we're in the application sector?
I mean, that's already you can already learn something, right? If you have activity or not, it's helpful to know.
Okay, I'm asking the audience: is this a true application or is it not an application?
Yes.
Yes. Okay, let's put it on. So you see how difficult, even for the expert, it is to put something on the application tree. Next one. Oh, you're gonna love it. Weather forecasting with quantum computers. You see how hard this is.
In the future.
At one
So I need
Not yet.
your thumb. I need your thumbs. So 4 up. Okay. By the way, this is a YouTube video. You can watch this or not. But we have
Of course, not now. Yeah, we are not talking about.
Yeah, exactly. Not now. I mean, I hope no one is watching videos while we are so entertaining. Okay, the next one is going to be a tricky one. Quantum AI.
Yeah.
Yes, yes, yes. So you would say quantum AI is an application. Thank you. So do we put it on the tree or?
I would put it on.
Okay.
You do.
Wow, the tree is growing.
It's not a general.
I don't
We,
know.
we look into that.
Look into that in more detail to understand.
Navigating vehicles without GPS by quantum sensors.
Yes.
Oh, we agree on that. You see the tree is growing.
But do you have neuromorphic computing also?
Wait.
Inside a joke.
I have more tricky ones. The quantum internet. Okay, can someone explain from you what it is? And I put it on the tree. You all said yes. I mean, someone
Yes,
should
so
know
for-
what the
so for-
quantum internet now is all
So
about.
for me, it's to have quantum computers connected by exchanging quantum information over longer distances.
Good. On the tree. I mean, we are very fast here. Next one. Oh my God. It's already on sales for $777. You can get a device that's removing electrical charges from the environment to give you more health.
No.
With quantum effects.
Sounds like the magnetic sensor to de-harden your water.
Okay. Now I got problems with the scotch, but so for all of you who might have bought this, please return this. By the way, I have to be more precise. It's 790 euros. And sorry, I don't need to pin this. It's here. Drug development using quantum computers. Okay.
Followed.
All right. 100% secure quantum communication. So you can't sneak or eavesdrop into the line.
No, that's it. No.
Yeah, I followed the lead.
Okay, so you need, it was like, I was confused.
Because I mean, what you can see whether someone has sneaked in. You cannot avoid that someone spy, but you know that someone has spied.
Yes, then we would basically bust that claim. And the last one was even tough for me to validate. There was a recent paper out, Quantum Gravity for Quantum Computing. Breaking news, reducing errors without adding complexity.
I don't understand anything.
I thought you can teach me because I read this.
Is it AI generated? Is it?
It's a they claim. It's a they claim.
paper.
It's published in a peer-reviewed article.
Okay, there have been more of those things in peer-reviewed, very high-level journals.
So we should.
We should read the article.
I tried. I didn't get it.
Point.
All right, so we hide this, maybe eventually we have something for the future. So you see how tricky actually it is even for experts to validate whether there is a ground truth behind an application or not using quantum. And that's, I would say, because we are not so used to quantum from our daily business. Now, Ariana, Joachim already touched this, but I want to ask you. There is a lot of, I would drastically call it bullshitting around by combining quantum with something that has to be financed. And because you combine it, eventually you get funding. You don't need to comment on this, but I would rather like, what would you recommend everyone here now? After this evening, we have a very talented group of additional quantum scientists here in the room. What would you recommend them? Should they just say, okay, time will tell, we can just ignore them and it's going to solve itself, or should we proactively react on that bullshit?
Well, it's an interesting question because, like this Finnish detergent, I have also other examples like quantum healing. This exists really, and people are asking for money, so please don't do that. But besides this, I can really comment on what I said before. So for me, it was really like a surprise. I discovered quantum computing by chance. But it's not that I opened a startup and I just start to do things. I really spent time discovering, studying, making an effort. And this is actually what we need. So yes, time will then select who is going forward and then who is just telling bullshit. But yes, making an effort and really study. This is I would say, the key, and not just claim that you have better solution or without really any basics, yes.
I mean, it was not about you, it was more like, I mean, Joachim told me, I mean, I'm constantly opening the newspaper and there is a mixture in my heart between puking into the paper and laughing about it. Because as someone who was in the field for a long time, it's sometimes hard to accept what's written. So the question is more like,
yeah,
what would you do, but rather how should we react as a community?
Yes.
Can I add to that? Because I think, I mean, this is not a new phenomenon, not at all, right?
Yeah.
I mean, 25 years ago, I worked on nanotechnology, right? Nanotechnology is something which was at that time totally hyped up. Everything was nano, right? Your bike was nano, everything was nano. It was used on everything to sell it, right? Nano for whatever. And people to some extent also get afraid because they didn't know what it is. So fear comes in also, right? People did not understand what is nano and also be able to differentiate nano. Mm-hmm. Because nano in the end just means small in the nanometer regime, but it can be a nanotransistor which is sticking on a wafer. It's not flying around. Or it can be a nanoparticle where you really have to worry about that it can be toxic, right, if you inhale it. So that already these type of things need to be really talked about, they need to explain, they need to be differentiated, they need to be understood. And so the problem is that often the journalism is very fast. And you are very careful, also an expert, to carefully say your words of what is reality and what is not reality, but the one you talk to doesn't get it. right? So then an article is written in the newspaper, which he said, I never said that, it's total bullshit what this person writes. And so this is something sometimes it's really very difficult to also as an expert control this, because there is too little knowledge on the other side. And so I really appreciate your comment before. I would recommend everyone here to also, you know, buy the book and send and give it to the you know, to the kid or to whoever, that more people study also technology and are aware of things and be more critical. But I think it's not a new phenomenon. We had the same thing with carbon nanotubes, right? Stuttgart is also famous for carbon nanotubes, right?
Fake news are everywhere.
Graphene, suddenly bikes were built with carbon nanotubes, right? So I think there is always this thing, but you only can counter it with more information, more experts talking about this, and also, you know, also this type of interaction and discussion to explain things in a simple way and make sure that people understand what it is about.
Maybe I will add something from the art perspective or artist perspective. Of course, I just a week ago I fell in love with a kind of nanotubes because they are looking so beautiful. They are growing. They're
the best materials.
Yeah, and it's very inspiring for me. But by the way, I'm trying to understand all the topic better, and I'm in the residency. I'm spend my time in Basel and the Basel University to learn more about quantum physics, to understand what I'm doing actually as a quantum artist, because not so obvious that I know what I'm doing. I'm just very often I follow some kind of advices by the scientists. But anyway, quantum art is a kind of curiosum still. It's nobody buy quantum art, nobody invest in quantum art, whatever. It doesn't matter, because the first people, their first artists, they're dealing with, they are passionate. They are doing this just for the reason doing art and be progressive and be avant-garde.
But if you look at it, I mean, you can also express some wishes here. I mean, you started a new field.
Yeah.
What would you see when you project yourself 20 years ahead? How would it feel? Does it feel like starting a complete new era of painting, or an add-on to existing mechanisms?
It's very complicated to look so far in the future. I suppose we even have no really a good function quantum computer to really. I have not enough qubits to connect them, to encode it in. To connect them to my pixel, for example, and in order to get a beautiful visual, it's a kind of speculation. I hope, but I don't know. And maybe, and if then that will be some kind of a next art style additionally to impressionism, surrealism, or AI art, whatever. But maybe quantum art will have a little bit more potential, because we are. This is just a kind of feeling of people like me. I have some kind of impression that we will be able to really not only push the boundaries in the art, but with the quantum technology, the quantum devices in the future, we will be able really to even to lift this box, this matrix, this surface, and not develop, but explore completely a new level of creativity.
You touched something beside opening a new box, but you touched something you were wishing for more qubits. I think this is a general statement that's out there. No, don't worry. So I'm not doing it that brutal now. But I'm coming more, I mean, we're here in the section applications and how much time we still need. Joachim addressed it quickly. IBM is putting a lot of efforts also financial-wise into this subject. Others are doing the same. Would you, Heike, say that looking not on Europe but on the outside world, where sometimes especially the venture capital scene is going completely crazy? I mean, we've seen investments that can't be justified by looking on financial matrices, right? When you see at these intensive financial rounds, would you say that they're substantial, or will there be, in your opinion, you also referred to other technological trends, are we expecting some, well, cool down phase, if I say it politely, or is some huge desperation because there is so much hope in this community, especially in the financial community, where startups are financed with not only millions but billions in the meanwhile, while we still have to run multiple years for getting such a device industry ready?
Okay, I mean, these are many questions you ask. We can actually discuss and debate it a bit more than an hour, I think. I mean, as you mentioned before, right? We have a very dedicated roadmap. We have over the last couple of years also delivered on the roadmap, and we have made and released this year a new roadmap for the next up to 2033, kind of, and where we promise 200 logical qubits by 2029. And that's a significant promise and statement.
Explain the difference.
Okay, so a logical qubit is an error-corrected qubit. And error correction in quantum is much more difficult than in classical. In classical, you can say, I use 3 bits instead of 1 bit, and then at the end, I kind of make a majority vote. So if I have some error in between, 1 bit flips, and I still have 2 bits which give me the right answer. Of course, you should not have randomness, right? You always have to have a certain decent error rate that you can do error correction. And in quantum, it's difficult because we have Heisenberg's uncertainty relation, we have probabilities, and therefore we can not only copy qubits, right? Because if you copy a qubit, you erase the quantum information, so you didn't gain anything, so you cannot do the simple majority vote, but you have to have more qubits in order to correct a qubit, or get a logical qubit. And at the beginning, with error correction codes, which were assumed, it was like thousands, 3,000, 4,000, 10,000 of qubits, depending on the error rate and your architecture. And we have made a big breakthrough last year where we reduced this by a factor of 10. And so we need about 288 qubits for 12 logical qubits. And that's significant because suddenly we can promise that we can get this done and really achieve 200 logical qubits by 2029. And then it's error corrected. This means you can run more complex problems because you can do more gate operations and thus can run more complex problems with these 200 logical qubits. And that's significant. Again, it's tough, right? It's a challenging goal to achieve it, but we are working on it very focused. And we wouldn't have put it there if we do not really strongly believe that we can achieve it, because meanwhile, these things also influence our share price, right? So it's not like a startup company. And that's a difference, I would say, also in what you can promise. As a startup company, you may be maybe a bit more légère in promising something, because you have, you influence only the startup, but not the big other business of IBM, right? It's not only, I mean, quantum is a small piece in IBM, so we have to be very careful on what we promise and how we influence. And I agree, there is lots of things where you say, oh my God, really? This is worth billions? And then you ask, okay, if I read the papers, and we talked about transparency before, right? If you log into our devices, then you see all the parameters, like coherence time, all the important parameters of a qubit and the performance you can see publicly, right? And in some of these startups companies, you say, okay, really, are they as far? It's not known, it's not published. And that, I think, and then also big companies sometimes, what you mentioned, right, have papers where you say, really? I mean, what you write in your press release is not really what you published in your paper. So where's the rest? So there are differences. And again, the problem is that in order to make this differentiation, you have to know a lot.
I see.
Point.
Strong statement. 2029 to remember, the first logical qubit. That's going to be Joachim. Beside being an outstanding scientist, you're also engaging for Europe in the context of quantum. You're leading the Quantum Baden-Württemberg initiative. That's the usual question, right? We as Europeans are looking towards these companies in the US that are making rapid progress, investing a lot. Can you give a bit of an overview to our audience what you believe about the European status on this maturity and the technologies?
Sure. One has to say that there is three, say, major, geographically, three major areas where quantum technology is going to be developed currently. This is the US, this is Europe, and this is China. Yeah? And these are three very different models of how to push technology forward. In China, it's basically top-down, and all the money comes from the government. It's channeled through basically very, very few people on top, and then it basically goes down to a few institutions. In the US, there is, because of the big IT companies, there is much private investment. There is VC and there's really capital in there, and this is driven mostly by those companies. The governmental spending on quantum is only 1/3 of what in Europe is spent on the governmental side, and this is the particular situation for Europe. In Europe, we don't have these big pension funds. We don't have the big IT companies. So here the technology is mostly, let's say, supported by governmental money these days, and this is on par with what is spent in the US when you add the private money plus the governmental spending, and the same in China. So at this point, I would say, while in AI, for example, I would say we basically have lost the race. Yeah? So this is basically happening in the US. In quantum technology, that's different. And this is what I always tell the politicians. They have to realize there is only very few technological fields where Europe is still, let's say, leading or basically on par with what's going on in the US. And we shouldn't give this away. It's our particular situation in Europe. We are a bit more fragmented. We don't have the big VCs, but the governmental spending on quantum has to compensate for this. No.
I see.
So this is the situation. So I'm really, in this sense, I'm optimistic as long as the politicians keep on track and realize that it takes some time. Just because you mentioned the car industry at the very beginning, yeah, which developed here in Europe and globally, as a mass product after Second World War. And of course, with the big car companies that we all know, but keep in mind the investment that the government spent on building up the infrastructure. Look how our cities look like, and compare it to how they looked like, say, 80 years ago. They are basically designed for cars, and this is governmental spending. And it was money spent to basically promote mobility, to promote industry, and blah, blah, blah. So the bottom line is government have to realize that in order to promote the technology, they have to be kept engaged and committed. Yeah.
This sounds like that we will have a second quantum computer with one logical qubit in 2029.
No, you see, the problem in Europe is that we need to synchronize. Now, this is always on a national level in the Federal Republic. We have this problem because we have a federal constitution, and in Europe we have the same problem because we are 27 countries basically, and it needs to be synchronized. But this also can be a benefit, yeah, because it allows to push forward different different branches, different ideas, and at one point we have to evaluate, we have to see, and we have to basically have an assessment what we actually promote and what not. But then definitely, I mean, there can be a European quantum computer, I'm pretty sure. Yeah.
I'm looking forward to 2029. Now, I think we're slowly coming to an end. I have one last flashlight, and because we're sitting around for now more than an hour, the next one is at least to say hooray or not. The question for the flashlight is, it's about how, as a society, are we realizing that quantum is now? Would you say there will be one day where it takes a big boom, it's going to be like the Rocky moment, and the day after the world feels different? Or will it be something that's silently sneaking into our life, that we are even not aware about, that it's going to change our life, we just adopt to it? So if you are for the big boom, you do it like this, and if not, you do nothing.
Can I do both?
Then we are entangled. So
Sneaking is...
you don't say anything, you just say whoop or not. You don't know? What would you guess, what would you wish for?
But it's something more in the middle. It's not that at one day you have everything, and not even on the other side that something is hidden and sneaking. I mean, people are becoming more aware of quantum, and we have to continue like this.
I will give you my reasoning for both. So on one hand, the reasoning for the applications which you wrote down here, I think they're really they will slowly come, right? Because it's not like the boom day and quantum computer will solve every application more energy efficient, more accurate and better so I think this will coming more slowly and we may not realize as much. But where I'm worried right now is that people will not realize that quantum computing is advancing very, very quickly. And there is one thing which we did not touch upon is the risk of quantum computing. Oh, you are touching upon it, but sorry to be faster. But this could make a boom, right? If you're not prepared for it, then it could make a boom. If we are prepared for it, it will not make a boom. And
It's your answer. I mean,
what I mean with that is to explain it, because so quantum computing. Okay, let's start differently. So the data which we use today is encrypted in a way that we use very, very large numbers, and we rely on the factorization of these large numbers, finding the prime numbers, takes a lot of time with a classical computer. That it takes hundreds and more hundreds of years to decrypt it. And that's why our data is safe. There has been the first proof that a quantum computer can do something useful by Peter Shor in 1994, which showed evidence, mathematical proof, that a quantum computer can do factorization in a very fast manner compared to a classical computer. And we already mitigate since 10 years doing lots of research in that, and there is new algorithms which are safe for quantum, post-quantum algorithms, which are standardized, but where I'm see that the people don't realize that these are coming fast and we have to use them starting now. And actually the Bundesamt für Sicherheit and also other countries, they have written reports and recommend that by 2030 you have all the important data already encrypted with these post-quantum safe encryption algorithms, which are, by the way, classical algorithms. They just cannot be accelerated and being solved by quantum computers. And by 2035, kind of everything, all our data, should be encrypted in that new manner. And there I'm a bit worried, because this could be a big splash if you're not prepared, right? If you're prepared, it's okay. But if you're not prepared, then that's why I have these two things.
So I have prepared yet again a sign, but the discussion clearly says that we, don't have the rocky moment. We don't have it like this. I think we put this sign like this because we still have to discuss.
May I add something? Because I mean,
Sure.
for quantum computing, I think my feeling is that at one point there will be this boom. There will be a device which will show that there is some practicability. But in quantum sensing, for example, think about a cancer patient who goes to a hospital and learns about whether the chemotherapy is successful or not after 3 months or 4 months, but after a couple of days. This makes a difference, but not a big boom in the newspaper. You know?
I already get reports that the discussion is very good. Let me put out the last one. I mean, when talking about quantum, we can look to infinity in terms of years and to an infinite amount of money that's going to be spent. But let's be more precise. So every one of you is now getting the snowball. And you can just have, so please restrict to 1 minute. But you already indicated, so I'm quite certain about what Heike is going to say. The next 5 years, what are you seeing in this snowball arising with the terms of quantum?
So we have already promised what we have to do within the 5 years, right? So it's very simple. And we hoped that, of course, then with this machine which we're building called Starling, we can really solve problems which create economic value. Less than a minute.
Well, I need to add something to what Eike just said. And I would really like to see that quantum is really utilized, for example, in pharmaceutical fields, that nowadays is still not possible, but with logical qubits, with more qubits or more resources, we get closer to this achievement, and this will really have an impact. This is, of course, one of the examples. Other examples, like in chemistry or even in optimization in transports, we are already doing something and testing quantum computing in all of this. But to really have an impact or a larger impact, we need to work on better algorithms, but also to get better hardware, better resources. So this is actually my hope to see in the next 5 years.
Okay, so I think, okay, I have to somehow. So first in quantum sensing, I'm pretty sure that we will see something in medical diagnostics and also in navigation, pretty sure. And the push for navigation is even harder these times now, yeah, because of jamming. We won't see an operable quantum fault-tolerant quantum computer. I don't think so in 5 years. I'm sorry to say so. And quantum communication is definitely something that is that will be strongly developed, such that it may become even sort of standard, at least among some critical infrastructure.
Should we speak about hopes or facts or some predictions?
No one can truly know what in 5 years is.
About communication, so this is my field, and so I really hope that we will find a kind of more trust by big companies, the owner of the big quantum computers, to get more access in order to produce to develop some projects, some art projects, pieces, and to communicate, to make quantum physics at least better understandable, because it's very complicated. It's a very complicated topic for us. I can paint a picture now to the end. It's for me, explore the quantum world is like enter a very dark room, probably very beautiful room, but I can desire to turn the light on and then destroy everything and see nothing at least. Because what I missed is I have a bad behavior, because the behavior is based on my routine, on my classical way of thinking about everything. And so I believe that the art can, with the art language, can really help also you to understand the quantum physics, but also make the quantum physics, and at least it didn't have to be not scary for quantum physics. And so what we need is, more logic qubits, access to quantum computer, and trust.
There is no better closing sentence. Thank you very much. Thank you for this very great and engaging discussion. This is your applause. And I'm not exactly sure what the protocol is, who's opening the buffet, but before doing so, there are comic items. And I was told, I can tell, they're free for gift. So if someone of you is interested in one of these cartoons, which obviously represent famous scientists from quantum physics, you can ask someone from the Leibinger Stiftung's team. I don't know whether you should just carry them away, but you actually can take them. Thank you very much.